Oh yeah, so we're going over section 29 of mod 3, is that right? Logistic, so we're talking about logistic regression. And so we're actually going to talk about this between this study group, and then next study group will be section 30, which will be going more into logistic regression and more like how to evaluate and say like, what is a good logistic regression? And at this point right now, you're like, well, unless you've read through the sections, you might not know what logistic regression actually is. And so it's kind of going up more of on our theme of classification, which is a big part of basically machine learning. And we kind of like, I keep debating about like, we haven't really said like, oh, machine learning, because like we've been kind of doing machine learning for the past while. Like linear regression is a type of machine learning. We also talked about, was it K nearest neighbors? That's a big machine learning algorithm. Logistic regression also is a machine learning algorithm that allows us to do classification. And so we'll kind of see what that is. And it actually ties directly, well, not, yeah, it ties pretty closely with linear regression, which is what we had before. So let me go ahead and start sharing my screen. So one day I'll get faster at this. Okay, cool. So you guys should all be able to see my screen now. That's just the GitHub repo. We're going to talk about it in a second. And go ahead and make this all small. Okay.
So controversy to make the editing more difficult.
Don't do this to me, Paul. I lost you guys though. There you guys are.
I see.
Okay. So, all right. So we have our logistic regression here. And so the main thing I kind of introduced it, it's going to be classification. So the main thing, like I said, how it's going to be used is classification versus a linear regression where we're predicting values. So if you remember with linear regression, we have our, what's it called? We have our line, right? Our line of best fit. That was created from data points. So like there's some data points around here and everything like that. And our line is some, well, it could be multi-dimensional, right? But like we'll say for 2D, it's a line. And so for example, this is like one of our features X, and this is our target Y up here, okay? And usually we denote this as Y hat. Y hat usually denotes like a prediction, okay? And if we had some value that was like, say, okay, well, we have some value of X right here. We'd say, okay, well, based on our linear regression, we just move that up, right? And say, okay, that means we predicted with a value of Y right here, okay? And so pretty simple. So we have a continuum, right? Where we can say, oh, as X increases, what does Y do? So Y increases at this level. And when we had multiple variables with multiple features, we can use that to predict more and more, like saying, okay, well, if X1 and X2 and X3 are all these different values, what is Y, and so on. So that's very different from classification if you think about it. Classification, we're really just saying, hey, what group is it in? We're not really looking at like saying what degree of what group it is. We're just saying, is it in this group? Is it in group A or group B? So remember back in like last week when we talked about K nearest neighbors, we might have a bunch of points over here. This is all 2D still. And a bunch of points over here, and we'd say like, okay, well, this right here is group A. This group right here is group B. And we say, okay, if there's a point like right here, a new one, it's like, what group does this belong to? So, well, it's probably part of group, B over here. So that's kind of the idea of classification. So again, logistic regression is playing off of more classification, but we'll use kind of the concepts of linear regression, and we'll see that in a second. Okay, so again, just recalling a little more of linear regression, we have this equation, and it's the generalized form of multiple linear regression, right? Where we have multiple variables, multiple features. Can you guys see that okay? Okay, good. So you can see like, we have essentially our intercept, basically. We'll usually have like beta 0, okay? And then our x1, right? This could be like, x, y, z, w, as going through all the different variables. And we have n different features here. So you can see here, we can also just write it like this. I like writing in this notation because it's just a super small. Note that if, in this case, x0 would just be, x sub 0 would just be equal to 1 by definition, so we can have this really easy. So there's no extra dimension. But this way I can just write it this way. Sometimes you can separate it out, but I don't like doing it. So anyway, we can write in this nice short little form, okay? So that leads us into using logistic regression. And so I'm going to show you the equation first, and then I'll explain like why are we even doing this. And so with logistic regression, you'll see it's very similar. We kind of use the definition for linear regression for that y hat in here. So it basically gives us the probability that something is this particular group. So you'll see I read it out as 1 over 1 plus e to the negative y hat, which you might be like, why are we doing this? And you're like, yeah, like we'll talk about this. But like there's a few reasons why, and we'll talk about it even for next section. But basically just trust me, say, oh, we got this equation because it works. And you can see here, it's like, okay, we have 1 over 1 plus e, and then we spread this all out. And then we can say, okay, well, it's the sum of all these parts. And say, okay, then we can put this all together. So this is being multiplied together. So you can kind of see like where the structure here is like, oh, we have this coefficient, e raised to the negative power of coefficient, same on side. So we can have multiple features. For the most part, we're only going to look at like a few features just to kind of hone in about what's going on. But the point is like this right here will give us a probability that based on the features of a particular point, if it's going to be in this group or another group. It's mostly a binary part. Now we can use logistic regression, kind of looking forward. We could use logistic regression for multiple classes. It's just that we have to do something called like one versus all. And we'll talk a little bit more about that. But just know that technically logistic regression has to be, by definition, like binary. Say, oh, it's either in this group or it's in this group. And of course, we can get around that by doing different kind of logistic regressions. But that's what it's meant to do. So I'm going to go ahead and go a little more mathy on this part. So the first thing I always like to think, like, this might be the more math side of me. It's like whenever I see equations like this, I'm like, what does this equation look like? How does it act kind of deal? So I kind of want to show you a little bit like what's going on here. So if I just want to say, okay, well, let's just, someone gave me this equation, 1 over e, oh, sorry, well, I'll put it like this. Okay, this equation right here. It's like, okay, well, what are the different values we can do? Well, we can kind of simplify this by multiplying by e to the power of y on top and bottom, right? So we can get like e to the power of y. And remember, y is like y hat, like it's this long equation, but it doesn't really matter. Like it's just some value, right? And we have like, okay, this would be 1 then plus e to the y. And so remember on a linear regression, when we had our linear regression up here, y hat could be basically any value because it's a line, could extend outward directly. Y hat could be from negative infinity to infinity, right? It reaches out those points. So it basically can go as high as possible or as low as possible, right? There was no limit in that sense, okay? So we want to see what happens when y is infinity, negative infinity, okay? And then a classic one's always like, hey, what happens when it's 0? But we'll check those parts out first. So when y approaches, and I'll be kosher here, when y approaches infinity versus actually being at infinity, okay? When y equals infinity, well, you can pretty quickly see, it's like, okay, well, it seems like it blows up. If you actually do the limiting case, when you do like the limit, and I'm just going to call this L, so I don't have to write it every time, but you take the limit of this L of y, okay, logistic regression, this ends up actually approaching 1, okay? And you can do the calculus in this and stuff like that, but just trust me, this, oh, approaches 1, and we can graph this out to actually show that it does do that. But when y goes infinity, basically approaches 1. Okay, well, let's see. And I think, in my opinion, negative infinity makes it's a little easier to see. So we have y2 approaches negative infinity of L of y. Okay. When that goes into negative infinity, in this case, we kind of just plug it in. It's just easier that way. So we have e to the negative infinity, 1 plus e, oops, it should be, yeah, that's right, to negative infinity here. And so if you look at this, if you remember anything about like, these powers and stuff like this tends to approach to 0. 1 over basically a very, very large number is close to 0. This number is close to 0, so we have 0 over 1. So essentially this is equal to just 0, that limit at least. So essentially it's like, oh, when we go to the very far negative, we go to 0. So you can already see, it's like, okay, it seems like, we have to check the middle, but it's like, okay, like we can see it goes from about like 0 to 1, okay? Maybe there's some weird fluctuation in between, but I'm gonna tell you that's the range it ends up going to. And then our last one is that if we actually say, okay, well, what happens when y equals 0? So when we have this equation right here, we say, oh, okay, we have e to the power of 0, which is just 1, okay? And then 1 plus e to the power of 0, which is also 1, okay? So that means you have 1 over 2, okay? So it turns out like, oh, when y equals 0, we actually get, what's it called? 1/2. Okay, so this kind of gives us an idea of what this function is, like what it's doing. And if we actually plot this out, which is probably the easiest way to kind of observe it, but I wanted to show you guys what happens in these limiting cases and kind of showing you some of that methodology of like how you might see it approached in like in papers and stuff like this. But you have these different limits. Essentially what happens if I have something like, well, I'll just call it L of y, which I know is not the best thing because now we have a different y, but L of y, this function right here, basically it goes from 0, and then I'll kind of take this curve upwards and go like this. Okay, and so this right here will be 1. It'll asymptotically approach 1, and then this will reach basically 0 as we approach negative infinity. So this is kind of like generally what this looks like. And this is the classic look of logistic regression. Okay, any questions on what this looks like, or like, you know, how I got these numbers or anything like that? No. Hopefully that's
Not yet.
Not yet. Okay, so I've got to clear this out. All right, so let's see here. The one thing is like, okay, before we implement it, I kind of say like, well, okay, cool, that's really nice, Victor, but like, I don't understand like how this is useful. And so let's kind of go through like a visual example of what this would do. So if we have our drawing here, I'm going to draw out our thing, and we're going to actually form a logistic regression on here. I won't talk about how we formulate the values, but we're going to just put in some points. So let's go ahead and just put some points, and let's say this x, let's first say like this x part, let's say this is like the weight of some like, I don't know, some person. Okay. And this y basically, it's like, oh, like we're trying to figure out, yeah, I'll leave this y to kind of be empty. But basically it's like, okay, this weight right here, this y might represent basically, are they, let's say they have heart disease or not. So yes, they have heart disease.
BMI.
No, they don't have heart disease. What was that?
BMI. It could represent BMI.
In this case, we actually want something that's more binary, saying is it yes or no. If you're doing a classic,
just ignore me entirely.
No, that's a good point though. It's like this has to be binary. So that's what we're actually going to say basically yes or no, 0 and 1. That's kind of what's going on here. So in this case, if we had to weight, it's like, oh, in this weight they do have, let's say, when they're under this weight, they don't have heart disease. They don't have heart disease. This person does have a heart disease up here. This person, when they're higher weights, almost all of them have heart disease. Maybe you have something like this. Okay, so you can kind of see, it's like, okay, like this is a general idea. So if you make a linear regression on here, what that would look like would be something along like this kind of equation, like this. And I'm going to throw in one just for the heck of it. That's kind of midway, just like right here. Okay, and so the idea here, we can use logistic regression, saying, okay, when you're at this weight, you have a pretty close chance, pretty high percentage of actually having heart disease. And then if you're over here, I'm sorry, not having heart disease. And if you're over at this weight, this higher weight, you have a much higher chance of actually being or having heart disease. Okay, and then if you're in this middle part right here, you're like close to about 50%. You might have heart disease, you might not have heart disease, at least based on this logistic regression model. Okay, now of course you can see that we have some misclassifications here, right? But we'll talk about those later. Now, just know those, okay, like based on this logistic regression now, we can say, okay, we can do 1 over 1 plus e, and then basically, well, I'll just have this like function part right here. Basically you put in like, okay, what is this weight here? This will give you some value, and basically that will tell you the probability that you have heart disease. That's my probability of heart disease. Okay, so that's kind of like the idea of what we use logistic regression for. Okay, so again, it's we'll talk about like how we figure out like what's the best logistic regression. Like obviously there's might be a better formula. Like for example, what it comes down to is this y hat right here, these values, these coefficients. That's the stuff that's going to matter, saying, hey, what's going to happen? But also there's a subtle part too, is that basically say, where do we cut that threshold of saying when someone has heart disease or not? And we'll talk about that in a second. But I just wanted to show you what this basically looks like and then how to implement this. Okay, so any questions on what I drew here? All right. So let me go ahead and we're going to go down to actually implementing it, which is always fun, right? So the first thing we're going to do, you'll see that I have sklearn. That's a pretty common package. I think the curriculum, the first time they introduced you, they use stats models, which is good. But I'm going to use sklearn. What's that?
I think we've used both in the curriculum.
Yeah, and I think the first one for logistic regression, they introduce it with stats models, and then the next like lesson, still logistic regression, they'll use sklearn. Just now, I'll tend to use sklearn because that's pretty common. Okay, so all I'm doing here is just importing some packages, right? So now I also got a data set right here, and this is a data set that's built into sklearn. It's a pretty famous one. It's the iris data set. It's actually the same one we used for k-nearest neighbors, but I just wanted to use the same data set. And so I'm creating a data frame just to make it a little easier and kind of similar to what the curriculum showed in their when they first introduced it. So just now I'm just putting the data in here and just getting the features name and everything. And then I'll show you what the data looks like. So you can see, basically it's based on flowers. So it's like, okay, the different lengths of the different, I don't even know what a sepal is, but like basically like different features of the flower, and saying the target, well, the target ends up being, if I were to do unique, it goes 0, 1, or 2, basically saying what kind of flower it is. And you can see some quick descriptions here. It's like the different values. So again, if I was really going into this, I'd probably explore this a little bit more, see what the distributions are, see if it's normal and everything. But we're kind of moving on just so we can see what classification it looks like. Okay. So the next thing we have to do is actually get my X, which is all of my features. In this case, I can use all of these features since they're all just numeric values. They're not categorical in any way. We can do things with categorical for logistic regression, but right now we're just going to stick with numeric. So thankfully everything's numeric, so we're just getting everything. And then of course we have the target right here. So again, just kind of slicing that so I can get it nice and easy. And then we have our testing and training. So again, our test train split, which is always a good thing. You can see I'm getting only 20% of it will be in the test. If you look at how many values there are, there's only 150. So this is a very, very small data set. So we're probably going to have a lot of issues, like in the sense of like how accurate it can be, depending on like how good the model can get. Just kind of knows like, okay, this is a relatively small, but same concept if you had a very large data set. Okay, so we have prepped our data, and now we're actually going to create a logistic model. So you can hear is that I'm using the sklearn logistic regression. Okay, and there's a couple things, for example, we haven't talked about this, but basically I'm passing this fit the intercepts, that way it doesn't have to worry about the intercept. I'm basically giving it some other values here. Again, these are things you don't have to necessarily worry about. There's a bunch of things you can look at. For example, you can see all of these different parts, all the different defaults. You can see there's quite a few in here, but we're not going to worry about that right now. Okay.
Wait, could you, what was the shortcut you used to do that?
Oh, Shift Tab.
Shift Tab. Okay, and that's like the same thing as doing question mark and running this up.
Yeah, though I think question mark. Yeah, I think question mark gives you a little more info because it gets the full, but this will give you the initial part.
I like that. Thank you. Shift.
Yeah, no
Shift. You said Shift Tab.
Shift Tab. Yeah, and just if you're on the, I believe if you're just on
that's nice.
On the function, it'll do that. I think if you're within it too. So just know like if you didn't miss it.
Okay. Yeah. Thank you.
Okay, no problem. All right. So yeah, logistic regression, that's from sklearn. So there's a few options in there. You can always play around with it. These are all like the different meta stuff that you need. And then we make this logistic regression classifier, and now it's all set. It doesn't have any data in it at this point, and that's when we actually create the model itself. And so we create the model basically saying, all right, go and take the linear regression line, or logistic regression classifier. You're going to fit it with the X train and the X and the Y train. Basically saying, all right, here's all the data for the features, and here's what they all should be labeled as, okay? And they'll learn from that. Now remember, this is all random too, so only 20% of it will be used. So it might not be perfect. It also could be really bad. Just depends on how things go. And then just know that if I print out the model, it'll give you some information about like what kind of, what the model looks like, and basically all the different values I have. So that's kind of nice what sklearn kind of tells you, hey, what kind of model did you set this up as? Right? So next we have is we basically say, okay, we have our model. So now we actually want to try to do some predictions. So we have our X test, right? And we'll call this Y hat, right? Our Y hat is our prediction, okay? And then we'll also do it on the training part, right? Because we want to see what the testing is, what the training looks like, and we'll go from there. So after that, Boyd's like, okay, cool. We actually finished the model. We saw how well we fit the model. We have our testing set. Now we actually want to see how well did it do. So first thing we'll look at is the training set. So there's a few things in here, but basically it's like, okay, we're going to find the residuals. So basically say how much did it in this case, the classification. So we want to see, did the Y training actually fit with our y hat train. So y hat train is what it predicted to be, either 0, 1, or 2, and y train is what they actually should be. Okay, so we want to see how well it fits, right? And you can see here in this case, we're just seeing the number of values correct. So in this case, how many were true. So it turns out of the 120 that we had, it was 80% of the data, 117 were accurately identified. Only 3 were false in this case. And you could explore a little bit more, say, oh, what was that? You can graph it out and observe a little bit more, see like what might be the reasons. But the point is, like, we did pretty good, right? In fact, if we did, this is kind of a fun one that the curriculum kind of shows, is that with your value counts, you can do normalize. So you can actually get percentage of saying, hey, what's the percentage of each one? So in this case, since we know there's only 2 options, there's 97.5% of the time it got the correct classification, at least in the training data. So it's like, that's pretty good, right? So it all comes down to like, well, training is good, but testing, that's what we really care about. We haven't seen this data yet. So now we're gonna say, okay, what's the difference between y test and y hat test? Okay, see how well it does. And we can see how well it predicted. All right, it predicted 28 out of the 30 correctly. 2 of them were wrong. And you can see about a 93% accuracy, right? So that's not too bad, okay? Now, there's a few caveats to this, which we'll get into in just a second. But when we do the evaluation, you might say like, well, okay, like we have this part, which just seems good, but there's a little subtle part to this is saying like, well, if we just guess, let's say there's only 2 parts and we just guess it, we could possibly do pretty well. Or one thing can happen is that let's say there's only, let's say you have like 1,000 data points, okay, and on your training, and like only 2 of them are like the no category, or like the binary no. Well, that means you can do pretty good accuracy. You can get like over a 99% accuracy just by saying everything is true, right? And so that's the case, like, well, we don't really want the model to do that. We want to kind of like adjust for those kind of things. So we can do some more evaluation. But before we continue on there, talk about evaluation, do you guys have any questions about how this was implemented, what's going on, like how we're classifying? Cool. Thumbs up then. All right, so I'll move on to the next part, which is more about evaluating classifications. So let me go ahead and close this. So we have a couple things in our tool belt, and the ROC curve and AUC are basically, what's it called? They're related to each other. So we can't basically do the AUC, area under the curve. We need to find the ROC curve or the ROC curve, okay? So like, kind of like what I was alluding to, we have to consider how well we can guess a classifier. So we need to compare, so what we can do, what we'll do in the ROC is basically say how is our false positive rate versus our true positive rate. All right. So this is kind of an interesting part. It's like, if you were imagining like you were, let's say like you want to see based on another person, you might ask like, what movies should I go see? Right. And maybe your classic was like, you find someone who's very similar to you, to predict what kind of movies you have. So you can go ask them and say, hey, what movies should I watch? And then that way you can kind of filter through what things you should watch. Right. There's actually the opposite of this is you find someone who's the exact opposite of you, who is awful, and every time they say, it's like, oh, this movie was horrible, it's one of the best movies possible. And so they have the exact opposite taste of you. Well, that person's actually a great classifier, right? You just basically just do the opposite of whatever that person says. And you ignore whatever they say essentially and just literally do the opposite. This is different from someone who's just a random person who will say random movies and sometimes they're good, sometimes they're bad, depending on the recommendation. This person's like literally every time they say it's a bad movie, it's a great movie for you. And if it's a bad movie for you, they'll say it's a great movie. So again, just kind of like saying like a worst classifier is like, the worst classifier is actually someone who says it just randomly, basically just complete guessing. And that's what we want to avoid. So
it's like people who like Wes Anderson and then everyone else hates him. I feel like that's a pretty good one. This time I nailed it. Love Wes Anderson, by the way.
You just throw enough examples, eventually you'll hit it, just like the random guesser.
Yeah, that's my strat.
Yeah, no, that's good. But like, exactly, like you would kind of say so we're not going to consider someone who is really bad at guessing in the sense that because they're so bad, they're actually good. We just care about like, what's random. So we'll tie that to logistic regression. So I'm going to kind of show you a little bit of, what's it called? Kind of a couple graphs on like how we would think this through. So imagine we have a logistic regression, okay? And we turn a continuous feature into binary. We have to figure out what's the threshold of saying this is actually true or not. So let me go ahead and graph this out a little bit. So yeah, that should be fine, enough space. So if I have my logistic regression like before, and I'll draw my guy like this. So there's my logistic regression. And it's not the perfect S-curve, but close enough, right? You guys get the point. So if I have my points like this, like these are all my different on my X values, right? Okay. These are all my different X values, what they should be. And maybe sometimes like we'll say this is yes, this is no. Okay. So here it's like, okay, well that would be mapped here. So I'll just make little dots. It'll be here, here. We'll say right here, right here, right here, right here. So here's the thing is that depending on how we write our threshold, we say, okay, let's say if they are like at that 50% right here, like let's say like really low. If we start off right here, it's like, okay, anyone who has a probability greater than, I don't know, let's just say that's about like 0.3. Okay, anything greater than 0.3, we'll say yes, this is all in the yes category. Okay, well, the thing is that this might be a false positive. So depending on our training data, this might actually be classified as no, you know, in our training. So we have to figure out, like, okay, what kind of threshold we have. So go, okay, like let's instead have a different threshold. Like, well, let's have a threshold that's closer to like up here. It's like, okay, well, we want to make sure we don't want any extra false positives. We only want to make sure we have true positives, right? But of course you might miss like someone right here who's closer. It's like, well, that should actually be classified as yes, but we're only getting this part right here. Okay, so basically we kind of adjust, and this right here, this line I'm drawing, essentially this threshold. Okay, the 50% line would just be like right about here. Okay, and that's usually kind of where we start from. But basically you keep drawing this threshold and you say, how many true positives am I getting? How many false positives am I getting? And you basically can classify it between that. Because ideally you want to basically not just get just the true positives, right? Your true positive rate, but you also want a low false positive rate, right? Because you don't want to accidentally misclassify something. Now, by nature, you can increase your true positive rate really easily. You just basically make this really, really small, this threshold, like 0.999999. So like you're really, really certain that someone, for example, has heart disease. You're like, oh, oh, you are, you know, let's say like in this case, the weight's like really high. It's like your weight is like extremely high, morbidly obese or something like that. It's like you probably have heart disease. But if that's the only people you say who have heart disease, then it's kind of a useless model in that case. And the opposite of this would say if everyone has heart disease, basically if you're not like a beanpole or whatever, basically like based on this model using just weight, there's other factors obviously, but let's say, oh, if you're not a beanpole, then you definitely have heart disease. So, well, that can't be true either. So you're getting a lot of false positive rate. So you have to find that middle ground and then what makes sense. And this threshold actually matters on the context of your data set. Basically, how much are you okay with a false positive rate versus a true positive rate, right? Well, we can actually graph this threshold and see how it changes. So going a little bit further, I have to clear out these drawings, otherwise I won't be able to draw more. Okay, so kind of going forward then, we can actually draw this graph representation. So if you imagine, and I'm gonna draw a couple graphs here. If you imagine this is our logistic regression right here. And then we have our different thresholds. So let's say this is our first threshold, our second threshold, our third threshold. We can actually talk about how good is their false positive rate versus their true positive rate. So we can actually do, for example, I'll just put FPR. So our FPR. So false positive rate, which can only go up from 0 to 1, right? You can't have a rate higher than 1. Okay, and then our true positive rate, 0 to 1 here. Okay, and basically what we do, we just take each threshold. So you say, okay, this very first threshold, oh, okay, well, it has a very low false positive rate, but also it has a very low true positive rate, which is not very good. So we like have a dot right here. And then maybe halfway through, it's like, well, okay, we have most of the true positives. The true positive rate's pretty high, but we're still getting quite a lot of false positives because it's like spread out that way. It's like, okay, well, in this threshold, we're actually getting a pretty good true positive rate, okay? And false positive getting pretty good too. So we might have a point right here. It's like, okay, well, this one right here, it might be at this point right here. So we have this nice kind of like these points right here for different thresholds. And so with these thresholds right here, we can actually say, okay, like this is like, we can kind of figure out what might be the best thing. Ideally, this is our ideal, right? Is our false, I'm sorry, I said that wrong. We want a low false positive rate, right? So our ideal is right here. So we want all the true positives and no false positives, okay? So you can see it's like, well, over on this card, it's like, this is not quite good. This would be closer to like up here because we're getting a lot of false positive rates. We're getting all the true positives, but none of the false positive, or we're getting a whole bunch of false positives. So again, you'd probably get something that's closest to here, and you can kind of try to figure out, it's like, okay, what's good, all right? So this leads us into, this is actually what we call our ROC curve. So this is me making it more continuous, but usually you'll see it as kind of like blocky because we're looking at different thresholds. We're looking at this threshold, this threshold, this threshold, this threshold, moving our way up through and graphing that part out, okay? So I can show you what an example looks like here. So, oh, I love this. I came across this not too long ago, and this shows a ROC curve. So no, you can kind of ignore this part right here. We can maybe talk about this, but we can adjust basically, well, no, we'll talk about this. So this graph right here is just showing like your prediction of saying, okay, these are all true, these are all false kind of deal. Or I'm sorry, this is all true, this is positive, this is red, and this blue is negative. And sometimes you might classify something that's actually true and false, and that's kind of what's going on here. But if I have this ROC curve right here, you can see those little parts, and I move this threshold, well, right here, I can make sure I get all, like basically everything to the left over here is false. So you can see my false positive rate is very, very low, but so is my true positive rate, which is no good. So if I increase this now, I can say, well, okay, if I make sure, I'm sorry, this is really throwing me off right now because I have it backwards in my head. So positive, so everything to the right is positive, is that right? Oh wait, is this low? Hold on, guys. This is low, this is high, okay. So, or is that right? Yeah. Because, okay, if I have it right here, let's go through this. Everything to the right here is positive, okay? So that means I have a very high true positive rate, or I'm getting the number of true positives I'm actually getting. So true positives over all positives is actually quite low. And then my false negatives though, my false positives is also very low because I never said someone was actually positive when they weren't. So that's why this is very low on this part right here, okay? So I can move this part right here. It's like, well, okay, as I move this threshold, you can see, okay, you can see that curve. And ideally, you can see this part, is that this is the ideal is right here, right? Where we have a very high true positive rate and a very low false positive rate, basically 1 for true positive, 0 for false positive. But if I move in this direction, well, in this case, my false positive rate is, sorry, my true positive rate, I'm capturing all of the true positives. You can see I'm getting everything on the right here will be declared positive, but my false positive rate is very, very high. Okay, so you can see my true positive rate is very high, my false positive rate is really bad. So you can see this threshold is pretty bad on the ends here, and at the middle is probably our ideal. And then I can see like, well, okay, let's say there's not very much crossover. Maybe I'm pretty good at like actually figuring out, it's like, okay, well, that means there's not very many crossover. In that case, you can see I get very close to 1. The only time I can actually get to 1 is if there's no crossover at all. But if there's any crossover, I will never get exactly 1, which is pretty realistic, okay? And of course, if I'm really bad, basically I'm taking a guess. It's like, I'm sometimes getting it positive, I'm sometimes getting it negative. You can see no matter what it is, this is a 50-50 chance, basically. This is like kind of the worst kind of model. This is our worthless model. Okay. Any questions about this? Kind of stumbled about for a second. Okay, cool. So I think this one would be good to actually show some code examples. So this right here is, I kind of took the concept from here from this, from scikit-learn, basically where sklearn comes from. They have an example here, but I kind of broke it down a little bit to something that we're familiar with. So I'm just gonna run all these stuff. Just know most of these things are like metrics and stuff, pre-processing, multi-class. I'm doing a couple things just to make it work, but just know that most of the time you would be able to do this without having to do multiple classes. I just wanted to show you guys that. So I have my iris data. Oh yeah, go ahead.
Quick question. Do you actually remember all of those imported functions up of the top?
Oh, do I remember it? No,
No.
I don't remember. Actually, I know most people, and I started doing this myself. You might use a text expander. So someone once showed me like they do a text expansion. So when they basically type in like, sklearn, they'll type like sklearn logistic, and it'll just fill in basically all the imports they normally would need for sklearn. Sometimes you can even like put in like your Jupyter notebook as a default, say, hey, by default, load all these libraries and stuff like that. For the most part, I don't know anyone who actually would be able to type in some of this. For example, like as you do more and more stuff, like if you're using the same stuff over and over, obviously like NumPy, you're not going to forget NumPy, how to import it. And usually what happens is that I will like start writing my code and I was like, oh, I need this library, and I'll actually bring it up here. So I'll go back and forth just to make sure I have it. So like, I was like, oh wait, I didn't put in the metrics. Okay, let me go ahead and put the metrics in here. And other times, I go look this up. Like, wait, how do I'm like, I know I need a logistic regression. Where's that coming
We've probably mentioned this too, but along that, so sorry if this is repetition, but along that same line, when when you're preparing like a J notebook, like we would for one of the projects or something, do you intersperse the libraries based on when you need them, or do you put them all at the top? Because I make the requirements file that has everything that I use separate.
And that's different. Then the requirements file will be more for you install it. I think it comes to personal preference. I think a lot of people put it like they separate them out into like where they are, like where they need them. So, oh, I'm now doing logistics regression, so now I'm going to import logistics regression here. Depending on what it is, I tend not to do that. And the reason why is because sometimes when I'm rerunning the notebooks, I'll kind of skip around. And if I forget to import that one.
Okay. Yeah. Your code won't run all the way through.
Yeah. Now there might be some cases, for example, if you import a library or doing some of the extra stuff right here, it might take a long time and you're never going to use it for that specific case. In that case, you might separate it out into separate cells, or, maybe bring it down there. I think in the end, it comes down to personal preference.
Thanks.
Yeah, no problem. And sometimes I'll put little comments here too. Say, hey, I'm importing this because of this regression or something like that. Cool. All right. Good questions, guys. So anyway, I have all these stuff right here. You can see the ROC curve, and we'll talk about AUC in a second. Basically, I have this iris data, the split right here, our training and test split. I have my classifier, logistic regression, like we saw before. In this case, I did multinomial because we have multiple parts, and this will be useful for us later. Don't worry about too much about how I'm doing this part. And then, of course, this is just to basically get in the format so I can use ROC. You can see in the curriculum how they do it, but also this documentation for like why this is, but I won't go into details exactly what this is. So basically just to reformat so it's easier for me to process through to find the ROC curve. And so we're not doing area right now, but just I have this saved up here. ROC, basically, we have this curve right here. We take in our test, we take in our score, and basically we're going to plot out, say, okay, like if we drew different thresholds, where would the logistic regression actually split it at? Okay, and just know that ROC curve, I kind of split this over real quick. ROC curve actually isn't necessarily just logistic regression, because it just means false positive rate versus true positive rate. Okay, so it can actually be applied to other classification. But since we're doing logistic regression, and that's our first one, it's kind of the most obvious one to deal with. Okay. So anyway, I run this right here, and you can see here is my ROC curve. In this case, for the class 0.1, because I can only put one ROC curve at a time, basically one versus not. And you can see here at certain thresholds, it's not very good. In this case, I actually did a really poor job in predicting it. If I look at another class point, which was one of the classes for, we had 0, 1, or 2 for our data, you can see the ROC curve is pretty good. Like we actually got it, like in this case, almost at 1. Our false positive rate is pretty low. And that makes sense because we only had 3 errors, right? For our training set, at least. And I think for our testing set too. So anyway, this is kind of like an ROC curve, but I kind of want to show you guys one that didn't do very well. And you can see it's pretty poor. Okay. Our next part though, right here. Oh, I think I put this one for all 3 of them. So you can see, you can barely see that green one. The green one, which is our class 0, is actually hits exactly, but our class 2, or I think our class 1 here in this orange, didn't do very well. We couldn't predict it very well, no matter what the threshold was. So maybe logistic regression was not good enough. Maybe we needed more complicated classification to get this well, or maybe it's just complete random. Okay, so again, this is really cool, but then at the end of it, it's like, well, okay, like you might have, let's say, I'm gonna draw this out. I have this logistic regression line, or sorry, my ROC curve here. But what if I do another model and I have an ROC curve like this? It's like, well, how do I quantify which is better, right? And you can probably tell, like, well, okay, clearly this is better, but like you can see that sometimes this data is loaded in a weird way, right? Sometimes you might not have something that's nice and smooth like this that's really obvious. You might have something that's a little like blockier and trying to figure out what this is. So we can actually use something called AUC, which is area under the curve. And so in this case, you're probably like, okay, the area under the curve, what curve we're talking about? We're gonna talk about the ROC curve. So all you basically have to do is essentially, well, the more area underneath this this curve, this ROC curve, the better that model was, regardless of threshold. Okay, so we can see really quickly, it's like the best kind of ROC curve is the one that basically is capturing a very low positive rate. So the highest theoretical ROC curve you could have, highest AUC for a ROC curve would be 1, right? Basically, all the way top here to here, 1 times 1. Area underneath that's just 1. The worst one right here, well, not the worst one, basically randomly guessing, would be this line right here, and this line would be 0.5. So basically, your AUC would range from 0.5 to 1. Now, ironically, like if you had like something that's opposite of that, that's like the opposite direction, like I said, it's kind of like your worst, like your friend who completely disagrees with you on movies. Well, in that case, like, well, technically you can actually flip it over and just basically reverse all of those trading points and get better. You usually won't get that because the way we do our training models, we're looking for the best fit. So we won't get something that's worse than basically just random guessing. Okay, so you kind of just know that's possible, but unlikely for you to actually ever see. Okay, so really our AUC will range from 0.5 to 1, right? So I'll show you some implementation here. And this one's actually directly from this code right here from sklearn or scikit-learn. And so just know that we're using a different classifier, which is not really important about what classifier we're using. It's kind of showing, oh, we can get a different ROC curve. And this one does a pretty good data set and a pretty good classifier, so we can actually see a little bit better. So I just run the same stuff like before, and then I'm gonna plot out the figure so we can actually see those parts, and you can see all the different ROC curves right here. So, and you can see in this case also the areas. So you can see, kind of makes sense. You intuitively probably know, oh, this orange one's not as good compared to this blue one versus this light blue one, this kind of awkward looking one. This kind of makes sense, is that basically some of the classes are classified better than other classes. Okay, so you can see the ROC curve for that aqua one is about 0.91. For the orange is about 0.6. So pretty, not that great, right? And then the ROC curve for this darker blue one is about 0.8 or 0.79. So you can see, so it's like, okay, you can start comparing, say, what thing can predict better. And this is really useful if you're comparing multiple models. So you're saying, oh, I have this kind of model that's doing classification. Let's say something like K nearest neighbor versus a logistic regression. You might say, okay, which model was better? And you have different ROC curves, and you can use the ROC curve to basically assess that model and say, okay, regardless of threshold, like where we make that cutoff point, we can see that's like, oh, the true positive rate versus the false positive rate wasn't very good. So yeah, so that kind of concludes our evaluation for this first section for 29. I actually think section 29 is pretty like they kind of introduce you to logistic regression, which I think is not too bad. Like it's one of the simpler models. Like, okay, there's either yes or no, and there's this function, which we'll see again actually. Basically this thing called the sigmoid function, which is that S curve. And basically it's like, well, you put in the values and basically say, all right, put in the features and say, all right, there's this value in here, and it predict the probability that says, oh, okay, like, are you in this class? Are you in this class? Or like, yes, this class, or not in this class, okay? And then with that probability, you can say, well, okay, where's the threshold? Basically, where do we draw the line there? And when we draw that line there, we actually create this ROC curve like we saw right here. We create these different ROC curves, and it's like, well, okay, how do you compare different ROC curves? Basically, maybe one logistic regression model is different from another logistic regression model. You can start comparing those different curves or different models with each other using the AUC. Okay, so cool. Any questions you guys have? Anything you guys want me to go back over, or anything you're thinking now? Okay, cool. And so one thing I think maybe a little subtle point that I didn't really talk about, which we'll talk about next section, is how do you figure out like how to do your parameters for, like if I look back at the equation, where am I? Right here. How do you figure out this beta, 0, beta 1, all that stuff? That might be kind of like, wait a second. Like if we're doing logistic regression, we know how to do it for linear regression. How do we figure it out for logistic regression? And that's the point where I think, like, if you think about it, it's like, wait, if we didn't really talk about that, I kind of said, oh, if we have these values. And that's what we'll talk about for next section, is like, hey, we can do this basically with our good old friend, maximum likelihood estimation, MLE. So we'll use MLE to basically figure out what's the best way to approach this, and what makes basically, what are these coefficients, what should those coefficients be, and how do we approach that? All right. Cool, guys. Any last questions?